outside of Chicago. There's the Fermi National Accelerator Laboratory, where I do a lot of my work, is another major accelerator lab that up until this year has been the largest accelerator in the world. And there's a separate control room at Fermilab to, again, monitor all the equipment going on at CERN. And just like, you go and get your x-rays at the dentist's office in the afternoon, and they are sent off probably overseas to some dentist in India or China or someplace, and they're being studied overnight, and by the time you come back the next morning, you have a full analysis of how many cavities you've got. In the same way, there are physicists in the United States working during the daytime for us, but that's evening for CERN. And so you have people able to collaborate and contribute to the operations of the experiments during what's daytime for them. I don't think there's yet a similar control room being set up in Asia, but if it was, then you could have a situation where the sun never sets in the Large Hadron Collider. It's always being monitored by someone, be it remotely, but someone for whom it's daytime, and then you don't have to be working through the night anymore, which is the typical norm for students in physics who have to go to work on particle physics experiments. Okay, so a lot of this is made possible because of the advances in computing and the internet. So what is it they're monitoring? They're monitoring what will be the world's largest accelerator. So that's a picture on my left here. No, that's my left. Yeah. Over there. Of the tunnel that's now 300 feet below ground. Those big blue things are the magnets that are steering a high-energy proton beam around in a circle. And you notice the tunnel kind of looks like it's veering off to your left a little bit. It's not a straight tunnel, it's a circular tunnel. And I should have a little pointer out. I don't have a pointer. Well, over here is a sort of map of the accelerator complex at CERN. And there's actually several accelerators. So a very high energy proton beam actually starts with a very modest proton beam, i.e. a bottle of hydrogen gas, and you zap it and you start making it go faster and faster until it becomes a very high energy proton beam. So in this picture it says sources in Linux. You have literally a gas bottle of hydrogen, and there's a small linear accelerator that ramps it up to a little tiny ring that accelerates the beam up to a modest energy. That's called the proton synchrotron booster. And then it goes into another bigger ring called the proton synchrotron, labeled PS. And it goes into an even bigger ring, gets up to an even higher energy in the super proton synchrotron. That's an accelerator that's existed for about 30 years now. And then it goes into this new ring called the Large Hadron Collider. And what's happening is that there's a proton beam going one way around the ring, and then there's a separate proton beam going around the other way around the ring. And about somewhere around the ring, they're brought in to collide. And these are very energetic collisions, and the idea is to create a really high temperature environment, kind of like what would have existed at the very beginning of the universe, kind of like the Big Bang. So this big thing is really big. This picture here is something that CERN publicizes a lot because it means a lot to people in Europe. That's the town of Geneva, and you can see lots of roads and farmlands, and in the background is Lake Geneva. And then they've drawn in red what the Large Hadron Collider would look like if it was on the surface. And of course it's underground, so you can't see it. To us, maybe that doesn't mean a whole lot, so I've drawn the same size circle on Austin, Texas. And kind of keep in mind, at the very top of that picture is where UT is, the little A from Google Maps up there. And at the very bottom of the picture is Austin Bergstrom Airport. So that's about the size of this accelerator tunnel. It's about 17 miles in circumference. So a very fast sprinter could probably get around the Large Hadron Collider in a couple of hours. The protons do it in about 10,000th of a second. They're moving at the speed of light. We're very close to it. So it's really, really big. That's why people call it the world's largest scientific instrument. There's never been such a big tool as this ever made. And it goes up to really, really high energies because these protons are resistant. So like I said, at several points around this ring, the protons are made to collide into one another, and these are really energetic collisions. The debris of junk that's coming out of these collisions, all those particles are also having tons and tons of energy. And if you want to record the splash that's created every time a proton hits another proton at that energy, you're going to have to stop everything and measure all the particles that come out. So the instruments to record those collisions are also huge. So there are two such instruments. One's goes by the name of Atlas, and the other one goes by the name of CMS. And don't worry about what the acronyms are, but these detectors are big enough that you can just barely see a little tiny person standing at the center of each of those two little apparatus. So right on that catwalk, the blue catwalk on the left picture, there's a man standing in a hard hat and a lab coat. The right-hand picture, there's another person standing on a gondola, on the yellow gondola there, and you can give you a human candlestick to judge how big these things are. These are huge apparatus, and they're built by literally thousands of people. So imagine lots of little Egyptians like us who've been building some little piece of this instrument and then flying it over to CERN where it eventually gets assembled. And literally this is assembling chips in a bottle, okay, because these things are deep underground. People have been building this thing for literally a decade. So imagine your PhD depends on that. And the kinds of things we're doing, well, this is a computer simulation of what a collision would look like. You just see a spray of stuff by eye. But they're looking for exotic things that would have been around at the beginning of the universe. We'll hear later about the Higgs boson and other things that go on at that time. But we were trying to recreate in the laboratory a sort of micro version of the Big Bang. I said earlier these beams have an energy of 14 TeV. Well, that's probably not a very meaningful unit to us because I don't know how many of us know what a TeV is. But TeV, the T stands for tera electron volt. Tera means 10 to the 12, I think it is, yeah. So what's an electron volt? Well, if you were to try to scale it to things that we do know, particles in a blast furnace operating at a couple thousand degrees Celsius, those have an energy on the order of an EV, a little bit less in fact. So I think of a blast furnace as kind of an energetic thing. A Tesla coil can zip particles up to even larger energy, actually, about 25,000 electron volts. And actually here, let me pause and say, I don't know if you've ever seen these Tesla coils, but these things get up to incredibly high voltages, 25,000 volts, and then they just can get these zaps of lightning that go across the air. And they're such a big zap you can actually hear it. And there's a group in Austin that has a pair of these things, and they literally play music. So these zaps play at different pitches if they want to tune them in different ways. And actually later in the semester, the department's going to have a big open house, to which you all are welcome to come. You can tour around some of the labs here in the building. But after that set of tours, the student physics group is going to host this Austin group called Architect that's going to have singing Tesla coils. Come watch this, what we try to show. Anyway, Tesla coils, still pretty modest energies. Some of you may have heard of a Van de Graaff accelerator. You can accelerate particles up to millions of electron volts, so that's 1 with 6 zeros with a Van de Graaff accelerator. And Fermilab, the lab where I work at outside of Chicago, goes another million of a million electron volts, so it's at 1,000 giga electron volts. That's big enough where when Fermilab does an accident and the proton beam goes the wrong way, it starts burning holes in things. Okay, so that picture with the little dental tool there, that little dental mirror, the person is looking at a hole that has been bored in the side of the ring by the proton beam when they actually lost control one day, and they actually lost several magnets, and the proton beam just kept on going right through a wall, right into dirt, and now you understand why proton beams are located 300 feet below ground. Well, CERN is bigger than that. CERN is 14 TeV, so another factor of 10 beyond where Fermilab is. And at that point, people get really, really worried because now you're really storing a lot of energy. And I remember when I was a graduate student and Fermilab was just turning on the Tevatron ring, which was this ring that I've been working on for all these years, there were various quacks producing theories where there's so much energy being stored and the collisions are of such high energy. Someone was worried that we were going to create black holes right there in the laboratory that was going to consume Chicago. None of us were too concerned, but the same people were then conjecturing when Brookhaven turned on an even bigger accelerator in the mid-90s that yes, we were going to be creating black holes again, and this time they filed a lawsuit. Oh boy, so when you get the legal system in the United States going, that's an even bigger deal. And then it happened again with CERN this year. So it turns out people got even more worried, and these are quacks still. So they filed a lawsuit, and sure enough, that's what made the media. Now, we don't really hear about scientific discoveries in the media a whole lot, but we do hear about lawsuits. And so this got picked up by MSNBC, it got picked up by the New York Times, and I found it amazing that they flatly reported on all this as if it was news, because frankly, it's all quackery. And I don't know if you found this to be the case in things you know about, but